Hello everyone, I'm Sebastian Y, and this is Managerial Economics. In this video, we're going to talk about multiple regression. In the previous video, we estimated a very simple demand function that only had one explanatory variable, which was the price of X. Back when we studied demand, we talked about how there are many different factors that influence the decision to buy something and therefore the demand function. Things like the price of other goods, income, and so on. For reasons we'll discuss later on, we probably want to include these kind of things into our regression, and therefore make a more complex demand model that looks something like this. We have our price of X, but we might also have some price of a different good, Y, and consumer income in there as well. We can use essentially the same techniques we learned previously to estimate this more complex demand function. Just like we've done before, our regression continues to assume that demand has a linear functional form. The important thing to remember about our multiple regression equation is that our coefficients, beta 1, beta 2, and beta 3, represent the relationship between each of these variables, ceteris paribus, meaning that we are holding everything else in the equation constant. So beta 1 is the relationship between px and qx while holding py and m constant. Same thing for beta 2, which is the relationship between py and q while holding px and m constant. However, anything that we do not have in the equation, that is, other variables that are still hiding out inside the epsilon, we have not held them constant. We'll come back to why that's important later on. For now, let's talk about how we calculate the regression coefficients. Just like we showed in the last video with a simple regression, estimating the coefficients in multiple regression also uses ordinary least squares, or OLS. The main idea is the same, to minimize the RSS. Remember that the RSS is the sum of the squared residuals, EI squared, for the entire sample. EI is the difference between YI and YI hat. YI hat is going to be determined by our estimated equation. Y hat is beta naught hat plus beta 1 hat px plus beta 2 hat py plus beta 3 hat m. So to figure out yi hat, we're just going to throw i's on all of our variables and then plug this whole thing into here and then plug that whole thing into here. And that's going to be our RSS. Ultimately, what that thing is going to look like once we do all that plugging in will be yi minus beta naught hat minus beta 1 hat pxi minus beta 2 hat pyi minus beta 3 hat mi, and all that squared. Now we minimize the RSS with respect to our four variables. This is done just like we did before. We take the derivative of the RSS with respect to beta naught hat, we set that equal to 0. We take the partial of the RSS with respect to beta 1 hat, set that equal to 0. We take the partial with respect to beta 2 hat, set it equal to 0. Take the partial with respect to beta 4 hat, set that equal to 0. 4 equations, 4 unknowns. 4 equations down here, 4 unknowns, which are our 4 beta hats. That doesn't sound like very much fun to me. You probably don't want to do that either, so we're going to let Excel handle it. But I still want you to know what Excel is actually doing when we click that button. I also want to point out here that unlike with simple regression, when we go to multiple regression, we don't have those nice clean formulas that I showed you in the last video to, so to speak, manually calculate the beta hats. Again, we're just going to let Excel do its thing. Back over here in Excel, we're going to go back to our data analysis toolpack. Click regression. We're going to leave the Y range the same. That hasn't changed. But what we're going to do is change our X range to be not just PX, but to be all 3 of our variables. What you want here is for those 3 variables to be in a continuous block inside of Excel. If the M column was over here in G, Excel does not like that. So just copy and paste it over so that everybody's in a nice continuous block. I'm going to use Control-Shift-Down to select the entire block of data. Again, make sure that labels is selected, and then we're going to run that regression. Again, for the moment, we're going to focus on the coefficients column here, and this is going to tell us what our beta hats are. Where it says intercept, that's beta naught hat. Where it says px, that's beta 1 hat. Where it says py, is beta 2 hat, and where it says m is our beta 3 hat. Just to drive this point home again, m is not 1.9. Beta 3 hat is 1.9. And same thing with all the others. We can then take those numbers and plug them right into our equation. Once we know values for px, py, and m, we can then plug those in and get a prediction for our quantity demanded. Just like we did before with simple regression, you should always be using cell references to do this. This means doing all of your calculations inside of Excel. Let's write down our estimated equation from our Excel results. We have quantity demanded hat equals beta naught hat, which is 1087.2, minus our beta 1 hat, which is 10.0, times px, plus our beta 2 hat, which is 9.2, times py, plus 2.0 m. From there, if we know px, py, and m, we can go ahead and plug those in and calculate our q hat. Just as with simple regression, you should always be using cell references to do this inside of Excel. The last thing we're going to talk about here in this set of videos is fit. The way that we measure the fit of a regression is with R squared. R squared is something you may have heard about before, and you might have heard that it's a really important thing to look at. We're going to talk about how to calculate it and what it can tell us, but we should always keep in mind what it can't tell us, and why R squared is not that important in certain cases depending on what you're trying to do. Before we calculate R squared, we're going to need to define a few other things. First is the total sum of squares, which we just call the TSS. The total sum of squares is a measure of the total amount of variation in our sample. So what we're going to do is take yi minus y bar, square them, and add all those up for the entire sample. Yi minus y bar is the difference between each individual y and the average. Remember that y bar is the sample mean. So how much does each one deviate from the average? That can be positive or negative, and then square those, making them all positive and adding all of those up. Notice that there are no beta hats anywhere in this equation. So the TSS is always the same, as long as the sample is the same. The actual regression coefficients don't affect this at all. Next, we have the explained sum of squares, or ESS. The explained sum of squares is a measure of how much of our total variation in y, as measured by the TSS, is explained by the regression. The way that we calculate that is to take yi hat minus y bar and square those and add them all up across the entire sample. Remember that yi hat is our predicted values for y based on our regression. The third and final definition is the RSS, or residual sum of squares, which we've already talked about, which we define as the sum of the squared residuals, which we can then write out as yi minus yi hat squared. Add all those up. As we explained before, the RSS is a measure of the total variation in y that went unexplained by the regression. So what we have is ESS, the amount of variation explained by the regression, RSS, the amount unexplained by the regression, and TSS is the total. These three things will have the relationship TSS equals ESS plus RSS. The definition of R squared is the ratio of the ESS to the TSS. This will tell us the proportion of the total amount of variation in the sample was explained by the regression. Based on the relationship between ESS and RSS, we can also write the R squared as 1 minus the RSS over the TSS. The more variation that is explained by the regression, the closer the ESS is going to get to encompassing the entire TSS. If 100% of the variation in y can be explained by the regression, then ESS will equal TSS, RSS will be 0, and R squared will be 1. So 1 is the highest r squared that is possible. If the regression fails to describe any variation in y, then ESS is 0 and RSS is the entire TSS, and we'd have an r squared of 0, meaning that r squared must be between 0 and 1. Let's go back over to Excel for an example. Looking at the regression that we just did, we can find all of those values that we just talked about in the regression output. For all three of the RSS, ESS, and TSS, we need to look at the SS column right here. TSS is right here at the bottom. RSS is the residual sum of squares, so that's the middle one. And then ESS, Excel calls the regression sum of squares. And that's this one right here. If we take the ESS plus the RSS, we can see that those come out to the TSS, so that matches up. To calculate the r squared, we take the ESS and divide it by the TSS. So our r squared here is going to be 0.924, and we can see that that lines up right up here where the Excel output says r squared. What this tells us is that 92.4% of the variation in quantity can be explained by these three variables. The remaining 7.6% is explained by some other factors that we have not measured. R squared is useful if what you're trying to do is simply predict outcomes based on observed data. In that case, R squared is worth looking at. But if what you're trying to do is think about what is the effect of one variable on another, then R squared is not really helpful at all. As we get deeper into the material on regression, we'll talk about why that is. For now, I just want you to remember that if somebody tries to argue their regression is the best one because of its high R squared, you have to think about the context of that statement. For one last illustration of R squared, we're going to move to another data set called house price. This sample consists of data on houses in the Boston area. We have the price, the size of the lot the house is on, the number of bedrooms, and the number of bathrooms. We're going to start out by just running a multiple regression. We are going to try to predict the price of a house, so we'll select this whole column as our Y range, based on the three variables we have, lot size, bedrooms, and bathrooms. So I'm going to select that whole thing and run the regression. We can see from our coefficients here that bigger lot sizes means higher house prices, more bedrooms means higher house prices, and more bathrooms means higher house prices. I also want to point out here that our intercept estimate is negative, and to remind you not to panic about that. Of course, a negative house price doesn't make sense, but you also have to think about what kind of values we would get for these other variables. All we need is one bathroom in the house to cancel out that negative. And of course, every house is going to have at least one bathroom. Checking out the R squared, we have about 0.47, meaning just under half of the variation in house prices can be explained by these three variables. What we're going to do next is go back to our data set and run a new regression. In this data set right here, we have 6 new variables, x1, 2, 3, 4, 5, and 6. I'm going to add all of those to the regression. So we're going to use our lot size, bedrooms, and bathrooms, and then all of these new variables in the regression. Click OK to run that regression. You can see here that some of our new variables have a positive relationship, some have a negative relationship with the price. If we go up to our R squared, it's gone up from about 47.3% to 48.4%. If all we pay attention to is R squared, we would come to the conclusion that this second regression is better. It explains more of the variation in house prices. The problem with this is that x1, 2, 3, 4, 5, and 6 are numbers that I randomly generated using a random number generator before I made this video. These numbers obviously have nothing to do with house prices in Boston. What this shows is that adding variables to a regression always increases the R squared, no matter how irrelevant the variables. When a new variable is added to a multiple regression, the worst thing that could happen is that there is no relationship at all, and it does not improve the fit. The R squared stays the same. It can never make it worse. But even random numbers will just by chance pick up on some variation, increasing the R squared, even though they've actually told us absolutely nothing about our question of interest. The takeaway here is just to be careful about using r squared. We'll talk about it more in the next set of videos. For now, that's all I have for the basics of regression. If you have any questions, feel free to let me know. Thanks for watching.